Electric motor secrets. Understanding the Lockridge device. Lockridge device major parts. During cleanup operations after the end of World War II, U.S. soldiers were doing house-to-house searches throughout Germany, to make sure there were no more enemy combatants left. Germany had operated under blackout conditions at night for months, so the cities would not be easy bombing targets. Likewise, most utility services had been completely disrupted and fuel was also scarce. This situation provided the inspiration for a brilliant engineer to provide himself a little bit of light in his own basement, with the windows totally shaded. When the U.S. soldiers reached this house, the machine was operating in the basement, running itself and lighting about 300 watts worth of light bulbs. What you are looking at is the heart of the machine. Lockridge device, coil assembly. The machine was based on a Bosch Automotive Generator, most probably taken from the limited production Volkswagen of the era. The stator windings were modified and their positions in the housing were altered. Slots were machined in the housing to separate the magnetics into two halves. One part was rededicated to the motor operations and the other half was left as the generator. The windings on the armature were not modified. The commutator brush assembly was also modified to adjust for the new coil positions and the new motor functions. The U.S. soldier who found the machine was named Lockridge. Instead of turning the machine over to his superior officers, he crated it up and sent it home to himself. Once home, in Boise, Idaho, Lockridge back-engineered the machine, built operational replicas throughout the 1950s, and sold them to weekend campers, to light their campsites. No working models survive today. Lockridge Device Research Notebook. In 1980, another resident of Boise, and friend of John Bedini, started trying to piece all of the surviving information together. This notebook is what this person, who wishes to remain anonymous, gathered in his years of work. The notebook represents an exhaustive search for facts, contacts, and eyewitness reports of the functions and appearance of the working machines. He never saw a working model, although he did find people who were known to have had working units at one point, but would not discuss their experiences with him. 30 years later, the trail of evidence is cold and most of the eyewitnesses have passed on. The remnants of the project were given to John in 2008. So, here is what we know. The Lockridge device includes a motor section, a generator section, a flywheel section, a capacitor, a 3-winding inductor, a bank of light bulbs 300 watts load, a modified commutator, an on-off switch, a pull cord to start the machine. So what is the problem? We are missing a few important pieces. No working model to back engineer. No pictures of a working model. No explanation why it worked. No theory of operation. No schematic diagram. No speculations on a schematic. Other details. The original unit was built from Bosch 6-volt generator, probably from early Volkswagen. Replicated units were built from a modified Delco, Remy 12-volt automotive DC generator from the early 1950s, used in Chevys from 1937 to 1954. The case was machined to produce a slot that isolated the magnetic field S between the two sides of the machine, motor and generator functions. A framework was built up around the case to hold the trifiller winding, 230 turns of number 21 gauge wire. A handmade capacitor was wound on top of the coil in the same frame, made from 2 sheets of copper, 30 feet long, with waxed butcher paper in between. Final details. The stator consisted of 4 wound coils, 2 large and 2 smaller, and were not configured symmetrically at 90-degree positions, as seen in the earlier photos. The rotor was not rewound. The commutator was modified to allow the motor to pulse once per revolution while still allowing the generator section to operate all the time. The motor brushes were modified to touch only one commutator section at a time. The light bulbs seemed to be a part of the circuit and could not be replaced by any other load. Lockridge device components. Pull cord start. DC motor. commutator, mass, DC generator, trifilar coil, on-off switch, capacitor, light bulbs. So, here again is the list of components for the Lockridge device, but this time, in graphical form. We can see that the mechanical parts are all connected, but what we don't know is the rest of the circuit. So, this is where our journey of discovery begins. Theory of operation. If the machine works, and we assume that it does, it must be getting its excess energy from somewhere. Since capacitors, coils, commutators, light bulb and wire are poor candidates for this energy source, we must look at the motor and generator components. Normally, motors and generators based on Faraday's direct induction principles are not considered capable of over-unity operation. In my educational film Electric Motor Secrets, produced in 2007, I showed that the efficiency of electric motors could be increased by modifying their back electromagnetic field behavior. So, the most promising of operation, from my point of view, is to explore the possibility of a low back electromagnetic field motor operation in the Lockridge device. If we can prove out that possibility, then we are well on the way to understanding how and why the machine did what was reported. DC motor cutaway view. There are more than a few people on the discussion threads who purport to understand what I mean when I say lower the back EMF of a motor, but from their posts, I know they haven't got the first clue of what I mean. In order to avoid any confusion, I would like to review the exact motor topology that we are dealing with here. The image here is a cutaway view of a DC motor. It has a wound armature, a brush commutator and a permanent magnet field. This is the specific structure of machine we will be discussing for the entire lecture. The only variation we will also discuss is replacing the permanent magnets in the stator field with coils of wire to produce the stator field with electromagnets. This is the universal electromechanical machine because if you apply electricity to it, it rotates as a motor, and if you rotate it mechanically, it generates electricity. Counter-electromagnetic field explained. In a DC motor, as the armature rotates, the armature coils cut the magnetic field, inducing a voltage of electromotive force in these coils. Since this induced voltage opposes the applied terminal voltage, it is called the counter-electromotive force or counter-EMF. This counter-EMF depends on the same factors as the generated EMF in the generator, the speed and direction of rotation, and the field strength. The stronger the field and the faster the rotating speed, the larger will be the counter-EMF. However, the counter-EMF will always be less than the applied voltage because of the internal voltage drop due to the resistance of the armature coils. The illustration represents the counter-EMF as a battery opposing the applied voltage, with the total armature resistance shown symbolically as a single resistor. What actually moves the armature current through the armature coils is the difference between the voltage applied to the motor minus the counter-EMF. Thus EA minus EC is the actual voltage effective in the armature, and it is this effective voltage which determines the value of the armature current. The first thing I would like to point out is that in these old books, what I am calling back EMF was referred to as counter-EMF. For the purposes of this lecture, you should consider these two terms to be identical, and that they both refer to the same phenomena. Second, I would like to explain that I use these old books because I find their explanation of things to be much more insightful. In fact, the newer editions of this same book are significantly rewritten, and I do not recommend any edition other than the first. So, let's begin. Definition of counter-EMF. Direct current motors. In a DC motor, as the armature rotates, the armature coils cut the magnetic field, inducing a voltage or electromotive force in these coils. Since this induced voltage opposes the applied terminal voltage, it is called the counter-electromotive force or counter-EMF. This counter-EMF depends on the same factors as the generated EMF in the generator, the speed and direction of rotation, and the field strength. The stronger the field and faster the rotating speed, the larger will be the counter-EMF. However, the counter EMF will always be less than the applied voltage because of the internal voltage drop due to the resistance of the armature coils. The illustration represents the counter EMF as a battery opposing the applied voltage, with the total armature resistance shown symbolically as a single resistor. So here is the symbolic diagram of the structure just described. We see the stator field on each side, designated as the north and south pole pieces. N and S, we see the voltage source here leading to the brushes. We see the commutator sections connected to the armature windings, shown as a single loop. And we see the resistance of the armature windings and brushes represented as resistor R sub A. We see the counter EMF depicted as a battery that develops a voltage in opposition to the external supply. And we see the current circulating in the armature winding referred to as I sub A. Does everyone understand this? This is standard motor operation theory. Okay. When the motor is just starting and the counter EMF is too small to limit the current effectively, a temporary resistance called the starting resistance must be put in series with the armature, to keep the current flow within safe limits. As the motor speeds up, the counter EMF increases and the resistance can be gradually reduced, allowing a further increase in speed and counter EMF. At normal speed, the starting resistance is completely shorted out of the circuit. Armature resistance is low. The internal resistance of the armature of a DC motor is very low, usually less than 1 ohm. If this resistance were all that limited the armature current, this current would be very high. For example, if the armature resistance is 1 ohm and the applied line voltage is 230 volts, the resulting armature current, according to Ohm's law, would be 230 amps. This excessive current would completely burn out the armature. However, the counter EMF is in opposition to the applied voltage and limits the value of armature current that can flow. If the counter EMF is 220 volts, then the effective voltage acting on the armature is in the difference between the terminal voltage and the counter EMF. The armature current is then only 10 amps. So, here is a graph that depicts what we just read. All units on the sides of the graph are shown as percentages of generalized maximum values. Ignoring loss mechanisms, we are just looking at functions and relationships here. With a steady applied voltage, light blue line across the top, the current is the highest when the speed is the lowest. As speed increases, the back EMF starts rising and the current starts dropping. At the maximum speed, the back EMF is the highest and the current drawn by the motor is the lowest. Here is the graph that depicts the torque produced by the machine. With a steady applied voltage, the torque produced follows the same characteristics as the current. So, torque begins at maximum and drops as speed increases until the torque produced is insufficient to cause any further acceleration. This point then defines the top speed for that applied voltage. The mechanical energy produced by the machine is seen as the red bell curve. Since power is the cross product of both speed and torque, we can see that the power peaks when the speed is 1/2 of the unloaded idle speed, and the torque is equal to the value produced when 1/2 of the maximum current is drawn. This is also the point at which the back EMF is reduced to 1/2 of its maximum value, as seen on the previous graph. This power peak is also referred to as the 100% rated speed for the 100% rated torque. We can also see that any further loading of the machine past this point reduces the power output and the motor's performance rapidly decays towards stall, maximum current draw, overheating and destruction of the motor if it is not saved by some fuse blowing or other circuit breaker. We are told that the best way to determine the efficiency of the machine is just to connect it to an instrumented dynamometer and run the test. By comparing the electrical input, measured in watts, as the cross product of volts and amps, to the mechanical output, measured in horsepower, as the cross product of the torque and speed, we can determine the efficiency by direct measurement. Efficiency by the book. Where 1 horsepower equals 550 feet lbs per second equals 746 watts. Mechanical energy output divided by electrical energy input equals efficiency. Example. 634 watts divided by 746 watts times 100 equals 85% efficiency. Losses by the book. Electrical power losses include resistance of the primary rotor and secondary stator windings, generally referred to as the copper loss, and calculated as current squared times resistance. Magnetic power losses include energy dissipated as heat in the iron core of the motor, and field strength losses as the magnetic field crosses the air gap between the stator and the rotor. Mechanical power losses include bearing friction, air resistance as the rotor turns, brush friction against the commutator, and more air resistance if the motor turns its own cooling fan. Stray losses include harmonic distortion of the power flow through the motor under load, flux crowding in the core material, and other magnetic leakages. So, this is what we were all taught, and not surprisingly, it's all true. None of this is the problem. The problem is that we have all been subjected to a sort of mass hypnosis characterized by a selective omission of information. This is what I call the New York Times version of how the motor works. In other words, we have only been told the equivalent of all the news that's fit to print. While this version of the understanding of how electric motors work has satisfied the vast majority of engineers for the last 180 years, it has also forced many brilliant people to accept some remarkably stupid answers for otherwise insightful questions. So, today, we must ask, how do we wake up from this intellectually deadened state of consciousness? Illustration of counter-electromotive force as a battery. Voltage source. Brushes. Commutator. Resistance of armature coil wire and brushes. Counter-electromagnetic field. So, now that we have cleared our minds, let's take a closer look at the nature of back EMF and try to understand what it really is. In this slide, which I showed you before, the counter EMF is depicted as a battery whose voltage is applied in opposition to the external supply. This reverse voltage is generated by the machine as it rotates, and is presented as a normal function of the machine. How counter-electromagnetic field lowers current. However, the counter EMF is in opposition to the applied voltage and limits the value of armature current that can flow. If the counter EMF is 220 volts, then the effective voltage acting on the armature is the difference between the terminal voltage and the counter EMF. 230 minus 220 equals 10 volts. The armature current is then only 10 amps. In this slide, which I also showed you previously, we can clearly see that the back EMF is the primary function of the motor that limits the flow of current. The implication here is that the back EMF is nothing more than a mathematical abstraction used to calculate the effective voltage, which in turn allows us to calculate the current flow value in relation to Ohm's law. From the way the book teaches it, the back EMF has no other characteristics worth mentioning. In other words, the back EMF is not involved in the calculations of the efficiency of the motor, and since it is only a voltage, it is not involved in any real power dissipation. The question is, are these assumptions true? Back EMF analogy. 3 batteries running a load, with 1 battery reversed. Applied voltage. 6 volts effective voltage running our load. 6 volts back EMF. Let's look at a real circuit put together like the back EMF example and see what actually occurs. Here we have a 12-volt power supply on the left that will act as our applied voltage, and we have another 6-volt battery on the right that will act as our back EMF. We also have a load resistor R sub L symbolized as a little light bulb and a current meter. If the resistance of R sub L is 1 ohm, and the back EMF is 6 volts, then we can calculate the current flow in the circuit at 6 amps, according to Ohm's law. With that calculation made, we can see that with an applied voltage of 12 volts and a current flow of 6 amps, 36 watts will be dissipated at the light bulb and another 36 watts will be dissipated charging the 6-volt battery, for a total of 72 watts dissipated from the supply. So, this is the first indication that the back EMF may not be merely a mathematical abstraction, or just a voltage, but may represent a location in the circuit where real power is dissipated or stored. Back EMF reality. Applied voltage powering armature winding. 12 volts applied. -6 volts back EMF. Both forward and backward EMFs are distributed evenly throughout inductor. 6 volts effective is proved by current drop, Ohm's law. This is the same example again, but this time I have drawn it more like the motor structure. If we assume that the total resistance from brush to brush, through the armature winding here, is 1 ohm, and the speed of the motor is sufficient to produce 6 volts of back EMF, then we can see that the system will draw 6 amps of current, like our previous example. But now we have a problem. We can see that the external power supply is providing 12 volts at 6 amps, or 72 watts, but the dissipation of power in the motor winding can only account for 36 watts, measured as the effective voltage times the current. The question has to be asked, what happened to the other 36 watts? We are told that the effective voltage is just a mathematical abstraction, and to ignore it. The problem is, that the machine behaves as if these conditions are very real. So this is the first anomaly we encounter. We know we must apply 72 watts to run the motor, but it is vitally important to understand if it only takes 36 watts to produce the motor torques, while the other 36 watts simply disappears into the machine and produces no other beneficial effects. Kirchhoff's second law. The sum of the voltage drops around any closed circuit must equal the sum of the applied voltages. Applied voltage minus back EMF equals effective voltage. Applied voltage equals back EMF plus armature current times the armature resistance. So let's review Kirchhoff's second law again. If we follow the formula given in the book, then the applied voltage minus the back EMF equals the effective voltage. What is interesting is that the book describes this in words, but never actually introduces the mathematical term for the effective voltage. E sub E, here shown in blue. In the second equation, we know from Ohm's law that E equal IR, so the IR symbol is in fact the effective voltage. The question is, why does the book refuse to introduce a symbol for the effective voltage in the equations? Now I'm no math whiz, but I can do arithmetic and simple algebra. So what's the problem here? Kirchhoff's second law simplified. Voltage rise number 1 equals voltage drop number 1 plus voltage drop number 2. Applied voltage equals back EMF plus effective voltage. Voltage rise number 1 equals voltage drop number 1 plus voltage drop number 2. Voltage rise number 1 equals voltage rise number 2 plus voltage drop number 2. So, let's simplify this a little. If we just think of the source voltage as a place where the voltage rises and the load as a place where the voltage drops, we might be able to understand this. Maybe. For Kirchhoff's second law to remain true, then the applied voltage must equal the back EMF plus the effective voltage, as stated. The problem is, in the actual machine, the back EMF is not a place where the voltage drops, but a place where the voltage rises to counter the applied voltage. So, if we subtract a yellow M and M from both sides of the equation, we get this. Kirchhoff's second law simplified. Voltage rise from the external supply minus voltage rise from the internally generated voltage equals voltage drop across the armature. Applied voltage minus back EMF equals effective voltage. So, Kirchhoff's second law is correct, it's just that the back EMF is a voltage rise originating on the opposite side of the equation from the applied voltage. From our previous analogy with the battery and the light bulb, we saw evidence that the back EMF acted as a location in the circuit where a portion of our applied power was dissipated and therefore, it was not available to light the light bulb, or in our real case, produce mechanical energy in the motor. I believe this hypothesis is also supported by the equations we have just reviewed. Physical analogy. 2 jet engines on a sled. 100 lbs 50 lbs resultant force is 50 lbs. Resultant force of 50 lbs moves through the 100-foot displacement. So let's look at one more physical analogy to try to sort this out, once and for all. So, if the 100 lb thrust jet represents our externally applied voltage, and the 50 lb thrust jet represents our internally generated back EMF, then the resultant force represents our effective voltage. Now we can see that to move the sled 100 feet forward, our big jet has to supply 10,000 feet lbs of work to accomplish 5,000 feet lbs of results, because our little jet has negated the other 5,000 feet lbs of work right on the sled. Apparently, this analogy also supports our hypothesis and suggests that one half of the power supplied to the motor produces all of the mechanical effects and the other half of the power is negated by the back EMF. DC motor back EMF profile. Amount of applied voltage destroyed by the back EMF. So, just to review, here is a diagram of the back EMF profile of one of our permanent magnet field DC motors. As we have seen before, for any given applied voltage, the back EMF rises as the speed increases. The back EMF is the least at startup and maximum at the full, unloaded speed. Maximum power is produced when the speed and the current draw are at 50% values, and this is also where the back EMF is approximately 50% of the applied voltage. DC motor effective voltage profile. Amount of applied voltage left to run the motor. Conversely, this is the diagram that depicts the effective voltage profile. It is what is left when the back EMF is subtracted from the applied voltage. So, we can see that Kirchhoff's second law is correct. At any speed a vertical line may be drawn down from the applied voltage value, and we can see how much of the energy is available to run the motor and how much of the energy is dissipated by the back EMF. Efficiency reconsidered. Efficiency equals mechanical energy output divided by effective energy input. At this point, we know we can't operate the machine to get this kind of performance out of it, but it is important to understand the possibility that the machine has always behaved this way, and that the back EMF has always been the largest loss mechanism in the machine, and that it is the actual function of the back EMF that masks this energy economy. If this is all true, there must be other evidence of it to consider, and there is. Summary of motor operations. If all real loss mechanisms are ignored for the moment, the motor appears to be 200% efficient. That is, if electricity is applied to the motor, it produces both mechanical force and electricity in inverse amounts. The overall economy of the machine is 1 in 2 out in varying proportions. DC motor operation. That is the real meaning if this graph. The machine is always a motor and always a generator, regardless of which of these functions may be defined as our preferred output at any given moment. When the machine is run in the middle of its operational window, the motor function maximizes its mechanical energy production when the generator function is only negating 50% of the applied electrical input power. But even this analysis leads to the erroneous conclusion that the machine is converting electrical energy into mechanical energy at some known rate. Summary of generator operations. The generator efficiency example is easier to understand. A mechanical input produces both a positive electrical output and a negative mechanical output. Again, 1 in equals 2 out. Generator operations. Applied mechanical speed. Reverse motor torque. External electrical load. Current. Here is a graph showing the generator operations. At any given applied mechanical speed, the production of current to power external loads is in direct proportion to the activation of the reverse motor torque, which makes the generator harder to turn. Summary of generator operations. In the generator example, it is easier to see, because the reverse torque on the shaft, activation of the function, demonstrates that mechanical energy is being produced in the machine in addition to the electrical energy output running the external load. Real machine operations. So, the efficiency of the machine is always 200% efficient, minus the real losses. The operator puts one amount of energy into the machine, either electricity or mechanical energy, and the machine produces two outputs, one electrical and one mechanical, and both of these outputs are of proportional magnitude. In the generator mode they are directly proportional, and in the motor mode they are inversely proportional. How is this possible? The machine produces motor operations when the magnetic field of the stator pushes against the magnetic field of the rotor. Magnetic fields can be measured in either Gauss or in ampere turns. In other words, torque in the machine is produced only by the movement of currents, irrespective of potentials. Where the law is broken. We were all taught that the machine converts electrical energy into mechanical energy, and that this mechanical energy production can only happen in a circuit location where current is moving through a voltage drop. This is apparently not true. The telltale behavior is most easily seen when the machine is operated as a generator. When a current flow is established through an external load, it still energizes the reverse torque production inside the generator in the windings where the voltage is rising. This clearly establishes the 2-for-1 benefit of the machine. The flow of current can not only power external loads, like light bulbs and heaters, but it also activates the reverse motoring functions of the generator and produces mechanical energy directed against the driving force. What it really takes. This means that mechanical energy production in the machine does not require the dissipation of electrical energy or the consumption of watts. It simply requires a movement of currents. This is not a mathematical abstraction. This discovery opens up the possibility of using these machines in totally new ways, with heretofore unheard of efficiencies. This is why regenerative electric motors can produce mechanical energy and recover most of their electrical energy inputs. John Bedini has been showing motors like this for years, but Ed Gray and Bob Thiel were showing motors that behaved this way as early as the 1970s. Torque charts for DC motors. Charts from motor manufacturer, Balder Electric Company. Here, finally, is my last piece of evidence for your consideration. These are the standard, published torque charts for 3 styles of DC motors, published by Balder Electric Company. The red dots are the points where the graphs cross at the 100% rated speed and torque, which represent the peak of the power bell curve. Now notice the torque values as the motors slow down. At startup, the permanent magnet field motor produces 650% of its rated torque. The series field motor produces 800% of its rated torque. And even the shunt field motor produces 275% of its maximum rated torque. So, the books say the motors produce significantly higher torques as the back EMF drops. So, here is our boring little drawing again, and now we can see what it really means. The machine is always both a motor and a generator. The orange line represents the motor functions of the machine and the red line represents the generator functions of the machine. The motor functions follow the current while the generator functions follow the speed. Remarkably, we are always told to avoid operating the machine where the motor functions predominate, and run it as a motor where the generator functions predominate. It's no wonder that they behave poorly. So now we can see where we want to run this machine as a motor, over here, on the left side of the graph where the back EMF is low. Counter EMF at startup. When the motor is just starting and the counter EMF is too small to limit the current effectively, a temporary resistance called the starting resistance must be put in series with the armature, to keep the current flow within safe limits. As the motor speeds up, the counter EMF increases and the resistance can be gradually reduced, allowing a further increase in speed and counter EMF. At normal speed, the starting resistance is completely shorted out of the circuit. So here is the book again telling us to keep the currents low when the back EMF is low. They recommend using a resistor to perform this function. The more interesting question is, how can we run the motor in this low back EMF zone safely at high speed? The answer is simple: we discharge a high voltage capacitor into the motor periodically, such as, once per revolution, and we store the momentum with a flywheel. Tesla's method of conversion. Not surprisingly, this process was developed by none other than Nikola Tesla and is the one of the many applications of his method of conversion. We can see the process in example number 1 where the generator charges a capacitor, which is then discharged through a circuit controller and into a motor, little box with an M in it. Pulse DC motor operations. In a motor designed to run on 1 capacitor discharge per revolution, the average current consumption goes up with speed, as does the torque production. As long as the capacitor is charged to a voltage that exceeds the back EMF by at least a factor of 10, you will always be able to put 90% of your applied currents through the machine to produce torque. The faster the motor turns, the more power it produces. Finally, we see a way to operate the machine that allows the motor functions to be fully expressed without the generator functions getting in the way. Lockridge schematic. Now that we understand the theory of why an ordinary electric motor may be able to produce excess mechanical energy, we can get back to the Lockridge device. Here is my proposed circuit. Pull cord start. 12-volt DC motor. Commutator. Mass. 240-volt DC generator. Light bulb 300 watts. Capacitor 208 microfarads. On-off switch. Trifilar coil. All of these conditions can be met by operating a motor, designed for low voltage high current operations, on high voltage capacitor discharges at 1 discharge per revolution. The currents are high, but limited in duration, so the machine will not overheat while producing high torque pulses. The input voltage is always 10 to 20 times higher than the back EMF, so the output is biased toward mechanical energy production and away from internal, electrical energy losses. Motor operations. Issues. Armature must be low impedance, capable of passing hundreds of amperes. Field winding must be high impedance, in order not to dissipate too much current. Capacitor discharge should not oversaturate core material with magnetic flux. Options. Primary candidate for this motor is a DC shunt motor, like an automotive starter from the 1960s. Field windings can be rewound for higher voltage operation, or fitted with a series resistor. Solenoid and engine engaging mechanism would need to be removed. Automotive starter for a 1965 Chevy 283. O'Reilly's Auto Parts, part number 030236X. This replacement starter motor costs $40 at O'Reilly's Auto Parts stores. Automotive starter interior view. Low impedance rotor wound stator coils 1960s vintage. This is the construction of such a motor. Notice the very large wire in the armature, the large commutator section, and wound field coils. Commutator operations. Issues. The function of commutator is to run the motor on 1 capacitor discharge per revolution. The commutator must be protected from unnecessary wear and from arcing during capacitor discharges. Options. External commutator can be fitted with 2 brushes and a single contact point on the wheel. Internal commutator inside the motor can be modified to perform this function. Creative options include disconnecting all but 2 windings on the armature and triggering the capacitor discharge with an silicon-controlled rectifier after the brushes are safely engaged. Generator operations. Issues. Since there is no battery in the system, the generator must be able to produce electricity just from rotation, to charge the capacitor. Upon discharge of the capacitor, the extremely high back EMF of the generator must be reduced to manageable levels. Options. The self-starting function of the generator suggests the presence of permanent magnet field, or a partially magnetized core material and a self-excited field winding. The current limitation necessary to reduce the braking effect of charging the capacitor can be supplied by a resistor or an inductor. 1/2 horsepower 180 volt DC generator 2500 rotations per minute. General Electric Model 5 BPA 56 kAg 10B, permanent magnet motor. If this machine is spun faster than the 2500 RPM rating, it will produce higher than rated voltages. Capacitor operations. Issues. The capacitor is the primary device that stores the energy from the generator and supplies it to the motor. When the original Lockridge device capacitor was hand-wound around the generator, this feature is not required for the system to operate. The capacitor is the total load for the generator, so it must be rated above the maximum voltage the generator will produce. Options. Capacitor should be placed close to the motor and the commutator elements, and connected with wire capable of carrying high currents. The capacitor must be capable of rapid discharge, similar to a photo flash type. Capacitor calculations. Assumptions. Machine will turn at 3000 rotations per minute. Generator will produce 240 volts DC at speed. Light bulbs need 300 watts. 3000 rotations per minute equals 50 rotations per second. Capacitor discharges once per revolution or, in this case, 50 times per second. 300 watts equals 300 joules per second. 300 divided by 50 equals 6. Each capacitor discharge must deliver 6 joules. Capacitor calculations continued. Formula for energy stored in a capacitor: energy equals 1/2 capacitance times voltage squared. Energy, in joules, equals 1/2 capacitance, in farads, times voltage squared. Capacitance equals 208 microfarads. So, this is an example of how to determine the capacitor values. Example of capacitor: Mallory 225 microfarads, 250 volts direct current. Capacitor is 1 in diameter and 3 long. Light bulb operations. The light bulbs serve the function of limiting the initial current surge from the generator immediately after the capacitor discharges. They run on a sawtooth wave whose true RMS voltage should not exceed their rated maximum. Options. Filament-style light bulbs can be run directly in this position. CFLs probably won't work. In the original Lockridge device, the light bulbs probably ran from one of the trifilar windings while one of the other windings was in the circuit between the generator and the capacitor. A step-down transformer could be in this position to run a large quantity of light-emitting diodes. On-off switch operations. Issues. On-off switch allows the unit to be turned off when it is running. Placement of switch in the circuit can control other starting features as well. Starting the machine requires rotating the motor generator while the switch is on. Options. Placement of the switch before the capacitor prevents the capacitor from charging when off. Placement of the switch after the capacitor prevents the capacitor from discharging when off. Trifilar coil operations. Issues. The trifilar coil functioned as an impedance matching component between the generator, motor and load. In the original Lockridge device, it allowed the use of the Delco-Remy generator, while making the least modifications possible. Its construction was 3 strands of number 21 wire, twisted together, and wrapped around the generator housing 230 times. Options. Choose components that are matched well, and ignore it. Use it to match components you have. Lockridge schematic. This is the most likely schematic for the Lockridge device. Think of this more as a block diagram, showing the relationship of the component parts. But I prefer this simplified version. Now some of you may be saying, this looks familiar. And it is. Here is the drawing from John Bedini's booklet, published in 1984, titled Free Energy Generator. Here we see an electric motor, a flywheel, a magneto-style generator, a capacitor, a battery and a special commutator. The battery pulsed the motor once per revolution and the capacitor discharged into the battery once per revolution. Comparison Lockridge-Bedini. As you can see, the machines are extremely similar. The Lockridge machine used a torque-enhanced motor driving an ordinary generator to run itself and light some light bulbs. The Bedini machine used an ordinary motor driving a drag-reduced generator to run itself and produce excess charge in the battery. For those of you who are finally catching on, there are obviously dozens of arrangements that work. Any design that allows for a torque enhancement in the motor or a drag reduction in the generator, or both, will allow for a working combination. Regenerative attraction motor and a flux gate generator, 1983. Here are 2 machines built in Santa Barbara, California in 1983. They are designed by me and built by Michael Knox, for our company Unified Dynamics, Inc. The machine on the left was a regenerative magnetic attraction motor and the one on the right was a mechanical magnetic gating transformer. These machines were built from our own resources, but when the company failed to raise more capital, the project collapsed before a fully self-running combination could be demonstrated. Of all of the machine combinations that can perform this magic trick, the Lockridge or Bedini type device is the easiest to make. In closing, I'd just like to say, for each of us, our interest in science started innocently enough. We were all inspired by the great halls of academia and told we could reach its heights if we studied hard and passed our tests. And all along the way, we were told of the great minds that had gone before us, laying down the laws of physics that were known and immutable. But the more we looked into these matters and thought for ourselves, the more things didn't quite make sense. When we asked our teachers embarrassing questions, we were told to shut up, because we didn't have the brains to question whether or not certain issues in science had been settled long ago. When we persisted, we were warned about what would happen to us if we went down that path. As our knowledge increased, some of us have had to live under a cloud of threats. Some of us have been visited by the men in black. Some of us have even had the stuffing beaten out of us. But all of this intimidation has been designed to serve one purpose: to postpone the discovery of what a free people will do when they work together to benefit the world with civility, cooperation, and compassion. Civilization began with the harnessing of fire and the invention of the wheel. We are now approaching the third great epoch in human history. We have looked past the veil and successfully determined the characteristics of the self-turning wheel. What we haven't discovered yet are the characteristics of a society that will use this technology with universal responsibility, self-restraint, and wisdom. For the benefit of our children, and our children's children, that quest must begin now.